When we're talking about energy, there's a couple of important properties of energy that are good to be aware of and that are useful properties that we're going to use as we start to look at energy involved with chemical reactions. The first one is that energy is what we call a state function. So let's explain what that means. This means that it's a property of a system, of a thing. We're going to use this word system to just describe whatever we're talking about, like a chemical reaction, that only depends on its state. Now, what do we mean by state? We mean just what are its characteristics. And in terms of like its physical properties, like what's its temperature? If it's a gas, what pressure is it at? The state would also be like how much of it there is. So the number of moles would be part of the state of a system. And how much energy is associated with a given system, it only depends on like what parameters are associated with it. It doesn't matter how it got to that state. So we can look at this with a sort of non-chemistry example. So let's imagine and thinking about potential energy, right? So energy only depends on state. So let's imagine we have a mountain. This is an example from your book. And there are two different skiers that are going to go up the mountain and then ski down the mountain. One skier just hikes straight up, or I should say not hikes straight up, but it goes up a ski lift. And the other skier hikes up a path that sort of travels back and forth, but they both make it to the same point on the mountain. So skier A and skier B. And they're right next to each other, and they happen to weigh exactly the same amount, so that their gravitational potential energy is the same. So even though they took very different paths to get from the bottom of the mountain to the top of the mountain, they have the same potential energy. They'll produce, so provided that they weigh their masses are the same. So what really matters is just how high they are up the mountain, right? This would be part of their state of matter, right? How tall is the mountain? We'll call it h for height. And that determines the amount of potential energy that they have. And so it doesn't matter how they got there. So we can say it doesn't depend on path. We'll rely on this property of energy and related variables of systems that are state functions to say we can imagine sort of whatever path we want to get there. You could imagine skier A, rides a rocket ship up or a helicopter up above the mountain and then parachutes down to the mountain. Once he's on that mountain, he's going to have the same amount of potential energy regardless, even though he did one path required a helicopter and a parachute. So the same applies to things like, you have a bunch of gas inside of something and it's at a particular temperature. If you have, if that gas started as a liquid and then evaporated but ended up at the same temperature, they're going to have the same amount of thermal energy. So this property of energy is what we call it, that it's a state function. So it doesn't depend on path, it just depends on what is the actual characteristics or properties of that system that we're looking at. And so that's one important property of energy as we think about it in terms of chemical systems. A second important property of energy is what we call the law of conservation of energy. And this is similar to the law of conservation of mass, which we've alluded to when we were thinking about chemical reactions. And this is that energy cannot be created or destroyed. So we can only transform energy from one form to another. So we can transform, for example, say potential energy into kinetic energy, but it doesn't just disappear, right? The energy will stay constant throughout the universe. So you'll have energy that maybe gets exchanged with to the surroundings of the system, but the energy never just completely disappears. It just changes form. It turns into a different form. One way we summarize this in what's called the first law of thermodynamics. And this states that any changes in energy, so we'll denote energy as E, and we'll use the symbol delta. This means a change, and this is the Greek letter delta. A change in energy, delta E, can only take two forms. So any change in energy is either work, which is, again, pushing an object or moving an object around, that definition of work, or it's heat, which we call Q. So work and heat. Now work we've talked about, but we haven't talked about heat yet. Heat is basically a way of talking about thermal energy. So heat is used specifically in science, right? We don't just talk about things are hot or cold, but what we specifically mean is it's the exchange of energy due to differences in temperature. This is the primary form of energy exchange we see with chemical reactions. They will usually heat things up around them or cool them down. That's also possible, and we'll talk about that possibility. So the first law of thermodynamics states that we can only change energy's forms, and if we look at both the system and the surroundings, which we'll get to in the next video, that energy won't be created or destroyed. It'll just change forms, either change from work to heat or heat to work or things like that. So this heat here, this is a way of keeping track of thermal energy, which is the kinetic energy of molecules moving around. And so those are a couple more things that we can talk about. Energy is a state function, meaning it only depends on the characteristics of a particular group of molecules or atoms, or a reaction that's happening or something like that. And this first law of thermodynamics and the idea of law of conservation of energy can't be created or destroyed, and it will only change in the form of work or heat.